We're in chapter 5, I think. So last time we started talking about nomenclature, and remember that really nomenclature is based on the type of sort of compound that you're dealing with. And really we'll have sort of two types of compounds. We'll have ionic, which is our metal and non-metal. And we really have molecular or covalent type of compounds, which are basically kind of two non-metals. Really, the difference, obviously, between those two is what we talked about with bonding. Obviously, one, there's no sharing of electrons. We get the transfer of electrons from our metal to our non-metal, creating our ions. And then the other one, obviously, is sharing of electrons. So really, depending on sort of what type of compound that you have, there's some different rules that we follow. We are, in terms of ionic guys, deal with either cations, which are our positively charged guys, which really come from the metal. And we have anions, which are negatively charged, which really come from our non-metals. And if we just have sort of these ions by themselves, there's a couple of different ways that we go about sort of naming them. The cations, we basically just use the whole name of the element. For our non-metals, we really take kind of the main part of the name of the non-metal. We do typically drop the last part, and we do put the IDE at the end of it. So non-metals always get the IDE at the end, and metals pretty much use the whole name of it. There's a couple of different types of ionic sort of compounds in terms of naming that we sometimes classify them as, and that is type 1 or type 2. So type 1 or type 2 compounds are both ionic. They both are metals and non-metals. And whenever a metal's pretty much involved in naming, it is really the most important thing to look at. It is really, for the most part, how you'll go about naming your particular compound. So it's always that metal that's really important. And in a type 1 sort of compound, the metal has a fixed charge. So that is our basically group 1, 2, 3, our zinc, our cadmium, our silver. So those are our guys that, for the most part in here, will make a fixed charge. And if you see them, then you know it's a type 1 compound. The good news about that is you really don't have to do much after that to name it. You just pretty much need to roll into the whole name and then the IDE there for the anion. Type 2 guys are pretty much everybody else there on the periodic table that's a metal. The metal will have a variable charge. And that is pretty much your transition metals. Obviously, except for these three. And also things like lead, like tin, etc. And that sort of area on the periodic table, they have the ability to make multiple types of charges. So although they're not technically transition metals, they are named basically kind of the same way as we name transition metals. And as we'll talk about that today, we do need to do an additional step when we name type 2 guys versus type 1. The other important thing is when we deal with an ionic compound is writing the formula, and the formula should always basically equal 0. So whenever you put anything that is positively charged together with something that is negatively charged, we should end up with really an overall charge of 0 to balance it out. So we want to do that in the simplest way. So, if you had some barium and you had some bromide, once again, when we put this together, we would need 2 of these guys here. Give us a -2 to balance out the +2. So BaBr2 would be the correct way to write that formula. The reason for this is, again, as we talked about, this is really for the bonding aspect of it. In order for barium to lose both of its electrons and get back to the noble gas configuration, it needs an extra bromine here to pick up that extra electron. Now, when we do write the formula, again, there's no charge, but it is, as we talked about, made up of two things that do have charges. So if you were asked to write the formula for the cation here, it would be the Ba2 plus. And if you were asked to write the formula for the anion, it would be Br minus. It would not be Br2 minus or anything like that. It would be just Br minus would be the correct one. In this case, if we were going to name this guy, calcium is group 2, which means it has a fixed charge, and bromine is non-metal, so it's ionic. And because calcium is group 2, we would just call it calcium bromide. And the form name, as we talked about, I think we don't use prefixes or anything like that. Would be the, I'm not sorry, barium bromide would be better there since we're using barium. That would be barium bromide. Same logic there. Had calcium in my head, but they're in the same group, so that's good. So barium is group number 2, so it still has obviously a fixed charge. So the proper name here obviously would be barium bromide. I think I use calcium a lot in examples lately, so this is in my head. Yes, sir. That's true. That's good. Other questions on that? So that's stuff we talked about, I think, last time. I think that's where we laid up there, right? We did the examples, right? That last example there with the name them and all that, right? Yeah. Okay. So we'll pick up from there. So let's talk a little bit about type 2 sort of compounds. So when we have type 2 compounds, as I mentioned before, it is still going to be ionic. And it's still going to be that metal and non-metal together. And once again here, it is that metal that's really important for us to determine it as type 2. And in this case, as I just mentioned, our metal will be found in the transition metal region, or again, just to the right of it, kind of underneath the staircase where we do have metals like lead and tin and all those guys. And the difference with those guys, again, is the idea that the metal can have a multiple or variable type charge. So when we do come across these sort of situations, again, the metal is going to determine how we go about naming it. We do need to figure out what the charge is on the positive ion. And we could do that because we will always know the charge on the negative guy, which is the non-metal. How we go about naming type 2 guys is pretty similar to type 1. We still use the whole name of the metal. We still do the non-metal with the IDE at the end, taking out the last part of the name. The additional thing that we have to do is actually use a Roman numeral here. So we use a Roman numeral. And what the Roman numeral tells us is the actual positive charge on the metal. So the Roman numeral tells us the positive charge on the metal. And what we mean by that is if you took one of the metals out by itself, what the positive charge would be on it, not the grand total of the charge, not how many metals there are, which is a very common mistake that people make when they use Roman numerals, is they think it tells you how many there is, but it tells us basically the actual positive charge on it. So if we take a look at our example here, we got FeCl2. Once again, I see a metal and I see a non-metal, which tells me it's ionic. Again, it is always the metal that you want to look at. And I see the metal there in the transition metal region, dead center almost, I think. And that tells us that it is type 2. So basically, what we have here is iron with some type of positive charge. The good news is you will always know the charge on what it's attached to. So Cl is group 7, which means it should have a -1 charge. And there are 2 of them, which means we have 2 of these guys. That gives us a grand total of -2 for the Cls. And remember, since it is ionic, we need to equal 0. So the iron here would have to be +2 in this case to balance it out. So it's got to be +2 there to balance out. Yeah. The Cl. Yeah. So remember, we talked about there are certain ions on the periodic table that make certain charges. So everybody in group 1 is +1. Everybody in group 2 is +2. And then because chlorine here is the right element this time, chlorine is group 7. Everybody there will make a -1, the nonmetals. Yeah, so that's how we know that. And again, that's really important with these sort of type 2 guys, because you could have oxygen, which again was -2, and then nitrogen, which is -3, and those type of guys. So because we can now sort of figure out our iron here, we would go with our name that we see there, which is iron Roman numeral 2. Once again, the 2 is for the positive charge that is on the iron. And just like in type 1, it doesn't matter that there are 2 of the Cls there. It has no effect on the name. So it is just iron Roman numeral 2 chloride. So once again here, we do not want to use prefixes or anything like that here. Definitely not with the Roman numeral. Now, the reason we need to use the Roman numeral is because iron, for example, can make multiple types of charges. That helps us distinguish between, say, that guy and if we had this guy. This again is iron's a metal. That's a non-metal, so it's ionic. Our iron again being type 2. In this particular case, we have not 1, not 2, but 3 Cl minuses, which is the -3. That means that the iron here would be +3 in this case. So that guy's going to be +3. And that means that this name would be iron Roman numeral 3 chloride. So once again, the Roman numeral there for the charge. So really the naming is just to let people know sort of in this particular case, we're dealing with the iron that has a +3 charge. In the previous case, we're dealing with the iron that has a +2 charge. We don't need to do that with type 1 compounds because type 1 metals have fixed charges. So when we see something like sodium, we always know that it's +1 no matter what the situation is. So you don't have to tell somebody, hey, that is +1. Same thing with our zinc, cadmium, or silver. They have fixed charges. So once again, we do not use Roman numerals with zinc, cadmium, or silver. Because again, when somebody sees that, it's sort of a known quantity that those guys have those sort of charges. But with type 2, because there could be some variable charging happening, we do need to sort of let people know sort of which one we're dealing with. Any questions on that there? All right, so let's take a second here and come up with the name here of the guy. Yes, sir.
People like to change the name of the metal instead of using the Roman numeral. So like you could say iron 2 chloride as ferrous chloride instead.
That is true.
+3, you could say ferric chloride.
That is true. We're gonna actually talk about that in just a second. Actually,
you can do that with practically any transition metal.
Yes, you can. Kind of use the old school name.
+3 is also the preferred state for iron as well.
Okay, so let's take a look at this. So PB is lead, which is obviously a metal. We have oxygen, which is a non-metal. So once again, this is going to be an ionic compound. We're going to look at the metal. So we do find lead not in the transition metal region, but it is one of those guys to the right that really does sort of follow the same path. It could have multiple types of charges. So we'll do our sort of thing here. And we'll do our lead. I'm not really sure, but I do have 2 oxygens, which each one is going to be -2 because it's group number 6 on the periodic table. That means in this case, that's a -4, which gives us a +4, which means this should be lead Roman numeral 4 oxide. Once again, does not affect the name. Now, I think the other day we might have talked about the idea that sometimes people are told, you could kind of just do like the crossover move to sort of figure out the charges and the names and stuff like that. So This is an example that if you did the crossover move, you might get the wrong answer here and call it lead 2. So again, you shouldn't blindly just kind of cross over the charges down and up. It will work in a lot of cases, but there are some cases like this one here that it really will not work correctly unless you understand sort of what's going on. So any questions on that? None there. And again, the 4 in the Roman numeral is for the charge. So as was mentioned just a second ago, there is sort of an older way of naming, and we're not going to use it in this class, but it does still pop up sometimes as you read things and stuff like that. So sometimes we will use sort of the older name for the element, kind of the historical name, like was mentioned there. For iron, it would be ferric or ferrous. And usually the one that ends in the IC has the larger positive charge. So ferric would be +3 and ferrous would be the +2. So it does pop up cupric and cuprous for copper pops up sometimes, and some other ones, but most of the time nowadays people will use Roman numerals, and we will use Roman numerals here. But just in case you sort of see it pop up somewhere, it's probably going to be sort of like a historical type name used, and if it ends in ic, it will be the larger positive charge, and if it ends in ous, it'll be kind of the smaller positive charge. Like cupric would be +2 for copper, and cuprous would be the +1 for copper. But here we'll strictly use Roman numerals for everything that you name. And here's a couple of other examples of that. So there's the cupric, the cuprous. Here's cobaltic, cobaltus. This is tin. And again, some of the older sort of naming, but we will strictly, again, roll with this. One kind of weird one is mercury. This guy here is mercury 2. And this guy here is actually mercury 1. So that's mercury 2. This is mercury 1. Oddly, the one with all the 2s is mercury 1. And the one with just the 1, 2 is mercury 2. That's because it comes as a dimer, and there's 2 mercury 1s put together there for it. So that's kind of a strange one. Sometimes people have a little trouble with. So again, our mercury here as well. All right, so as I mentioned before, to name these guys, we're going to again roll with the exact whole name of the metal. We're going to insert a Roman numeral to indicate the positive charge on the metal, and then the IDE at the end of it. So we got cobalt, which is a metal. We got CO, which is a non-metal. So again, that tells it's ionic. We want to look at the cobalt, which is the metal. Again, we see it in the transition metal region, which tells us it's type 2. That also tells us that perhaps, we need to figure out what the charge is. Looking at what it's attached to is group 7, and there are 3 of them. Each of them would be -1 because they are group 7. That gives us a -3, which means in this case, our cobalt should be carrying a +3 charge. And that means that we'll use the whole name there of cobalt. We'll use our Roman numeral 3 once again for not how many we have, but the actual charge. And again, this 3 has no effect on the name. So this would be chloride at the end. Any question on that one there? Looking at the next one, we see Cu, which is copper, which is a metal. I, which is a non-metal iodine. Once again, it's going to tell us it's ionic. Looking at the metal, which again is in the transition metal region, tells us that we should figure out perhaps what the charge is on it. In this case, we have 1 iodine, which is group 7 and -1. So in this case, it needs to be +1 to balance out the charge. This gives us whole name for the metal, copper. Here we use a Roman numeral 1 for the positive charge, and our non-metal gets the IDE at the end of it. Any questions on that one there? Lastly, here we have SN, which is tin, which is a metal. We have BR, which is a non-metal. Here, the tin is not a transition metal, but it is one of those ones kind of to the right and below the staircase that basically kind of fall under the same umbrella in terms of naming. So it can have variable type of charge. So once again here, our tin will have some type of charge. We look at what it's attached to. That is group 7. And again, if it helps, you could just draw them all out if you like. And that is a -4. That means that here the tin is carrying a +4. And our name here would be tin Roman numeral 4 and bromide at the end here. Any question on any of those names? All right, so rolling on the other side where we want to write formulas, I see iron, I see sulfur basically, which is a metal, non-metal, tells us it's ionic. And truthfully, when you see the Roman numerals, it tells you it's type 2, which tells you it's ionic. So as soon as you see those Roman numerals, you basically got a positive, negative guy you got to put together to equal 0, basically. The good news is the iron numeral 3 tells you the iron +3 is what the Roman numeral means. And has a -2 charge. So once again, we want to put this together to basically equal 0. And the common number there is going to be 6 to do that. We need irons to do that. So if we had 2 of those, that gives us +6. And we need 3 of the sulfides there to get us to -6. And that would be our proper formula there. Any questions on that one there? Same thing here, seeing the Roman numeral tells us exactly what the charge is. So that's going to be lead with a +2 charge. Our nitrogen is group 5, which means that's a -3. So once again, when we put this together, we want to equal 0. So again, here it's going to be 6 is going to be our number. So PB, we need 3 of them. And we just need 2 of the nitrogens there to get to 6. Again, if you drew it out, 3 + 2s is +6, and 2 - 3s is -6. Any questions on that one there? Lastly, chromium, Roman numeral 4, tells us our chromium is a +4 charge. And iodide is group 7, which is a -1. So in this case, we actually need 4 of these I minuses to balance it out. And that means CrI4. Any questions on any of the names or formulas here? All right, so you do need to obviously be able to go both ways, name the formula, formula to name. Again here, Roman numerals, absolutely positively, no prefixes here. So if you find yourself Roman numeraling and prefixing at the same time, you're probably writing something wrong. Yeah, so it shouldn't happen. Only one small spot where it could happen, but it won't happen in a normal situation. So a reminder, a couple of things as we talked about, Roman numerals are not needed for our type 1 guys, which is group 1, 2, and 3, zinc, cadmium, and silver. And then pretty much everybody after that, we do need to lay up some Roman numerals there for our charge on the metal. All right, so I want to try a few more here. So for each of these, why don't we give the name? See what you come up with. Okay, so let's see how we're doing. So starting with the first one, metal, non-metal there for our oxygen, mercury in the transition metal region, which means we do need to figure out the charge here. The oxygen is -2 because it's group 2, which means the mercury here is +2. So this would be mercury, Roman numeral 2, and oxide. Now you might be wondering, how would you know if maybe it's mercury 1? You will kind of see the extra 2 on the bottom there as well. So that's how you kind of know it's the mercury 1 type of thing. In this case, we have magnesium, which is a metal, Br, which is a non-metal. Here, the magnesium is group 2, which means it has a fixed charge, which means all we have to do is use the whole name there. So that's going to be magnesium. And our last guy there getting the IDE would be bromide in this particular case. Magnesium being +2, which is why we have 2 of the Br minuses there to balance it out. Looking at the next one, which is lithium metal, oxygen. Looking at the lithium, which is important, it is group 1, which once again means it has a fixed charge. So we could just roll right into the name. And this would be lithium. And oxygen becomes oxide. And lastly here, Cr, which is chromium and fluorine. Chromium is a transition metal. So once again, we'll do our quick little kind of figure out the charge Here our F is group 7, so it's -1 each. And there are 2 of them, which gives you a -2. So that is a +2 there to balance it out. And that would be the whole name here. So that is chromium, Roman numeral 2 for the charge. And again, even though we have multiples of the F's, it does not affect the name, no prefix or anything like that. Yeah. Yeah, so type 1, it's all about the metal. So whenever a metal's there, that's the most important thing to look at. And it is the metal that you want to look at. And if it is type 1 on the periodic table, it'll be in group 1, 2, or 3, like aluminum, or it'll be zinc, cadmium, or silver. So those guys pretty much have fixed charges. And that's how you know it's type 1. You don't need a Roman numeral. For type 2, is pretty much everybody outside of that, which is really our transition metals, the metal. And just to the right of the transition metal, where you find things like lead, tin, in that sort of area underneath the staircase, those guys tend to have variable types of charges, which means you do need to include the Roman numeral. Yeah. Yeah. I believe so, yeah. So this was sort of a combination of both. So all of those were type 2, the previous ones, yeah. They all ended up with Roman numerals. So that's definitely how you know it's type 2, yeah. Other questions on that? Okay. So here's a little decision tree to help you decide type 1 or type 2. And as we just talked about, pretty much it is the metal. We got a fixed charge versus basically a variable charge if you go the type 2 route. So transition metals to the guy to the right, group 1, 2, and 3 to the left. Yeah. You do not for anything that's a type 1 metal, because it will, for example, sodium is always going to be +1 no matter what the situation is for us. So you don't need to tell somebody that's +1, because it's kind of like known it should only be +1. And that's different than something like copper, where it has the potential in certain cases to be +1 or +2. So you got to kind of tell the person, in this case, we're dealing with like the +1, or that we're dealing with the +2, which is where the Roman numerals come into play. So if it has a fixed charge, no Roman numerals. And that includes, again, zinc, cadmium, and silver, which are technically transition metals, but we don't use Roman numerals for those for the same reason. Yeah. Huh. I'm going to say yes. Not that we'll use some weird ones, but the ones that we kind of commonly come across are things. Yeah, as it might sound weird. I guess to the left, to the right, and kind of like the top middle to the right and down, where silver, cadmium, and all those guys are. Probably to the left of that, or TA, W, MO. We probably won't have too much of those guys, but kind of all the ones we've sort of seen or talked about and stuff like that. So yeah. Other questions on that? Okay. So then let's talk about type 3 compounds. So type 3 compounds are different. They are covalent compounds, are molecular compounds. And basically they are sharing electrons here. And with our type 3 guys, they do contain only nonmetals. They are, I think, the easiest to do, but they are the ones that people kind of screw up the most on. And this is actually where prefixes should be used. So here we do use prefixes. And like mono is 1, di is 2, tri is 3, tetra is 4, penta is 5. We have a table coming up, I think, of it. Hexa is 6, hepta is 7, octa is 8, maybe nona is 9, a little deca action maybe for 10. And we do use prefixes here. The nice thing about this is because they're sharing electrons, there are no ions involved, which means we don't have to figure out charges or anything like that. Pretty much all you need to figure out is how many of each of the elements you have. So once you see the 2 nonmetals, you should be able to name it, pretty quickly. You're just counting basically how many there are in the formula, for example, and you don't have to balance out anything or balance out the charges. So the way that we use this table is, I'm not sure if that's the same table nowadays, so I'll cross it out just in case. But we basically use the first name of the first element. So we use the whole name of the first element. So basically what we do is we take the appropriate prefix and the whole name of the first element. Then we take the appropriate prefix for the second element. And that guy gets named just like we were doing as a nonmetal that has the ending changed out to IDE. So prefix whole name, prefix IDE at the end of it. There are a couple rules that we sort of follow when we're doing this. The one major rule is we do not use mono on the first name, but we can use it on the second name. So it's okay on the second name, but we don't use mono on the first name. So for example, CO, that is 1 carbon is a nonmetal, 1 oxygen, which is a nonmetal. We do not use mono on the first name, so we would just use the whole name of it, which would be carbon. But you can use mono on the second name, which would be monoxide, which leads us to the second thing that happens when we use prefixes, and that is we sometimes get a couple of vowels that roll up on each other. So we get like a and an O, or an O and an O. Typically speaking, we get rid of the vowel from the prefix. So here it's not really carbon monoxide. We get rid of that, and the proper name here would be carbon monoxide. So those are really a few of the couple of rules that are important. Mono can be used on the second name, no problem, but not the first name. And we do typically get rid of like the vowel when we get an A and O or an O and an O that comes together. Yeah. Exactly. Yeah. So that's how you know, as soon as you see both nonmetals, that's like, cool, I don't have to balance anything. You just roll right into the name. They really probably should be like the fastest ones that you name, because you're basically just counting and using the appropriate prefix. So there's nothing else to kind of figure out when you do it. But that definitely is how you know it is just 2 nonmetals together. Yeah. Now, a couple of I's are okay. So you get an I and I, it's okay in terms of a prefix, but usually the A and the O and the O and the O is the ones that we sort of get rid of there. So here's our prefixes as we talked about there, and our awkward sort of naming. We also talked about, I think at the beginning, that there are certain things that we do follow kind of common name for, and that would be our water here. So again, if you see H2O, that is what you should put water. It's not a trick question. If you see NH3, that again is ammonia, which is not to be confused with the polyatomic ion we'll talk about here in a second. And CH4, which is the simplest organic you could have there, which is methane, ANE. So those guys we do go by common name. Everybody else you could kind of use this way of naming. Once again, here we're getting rid of that A and O there in the prefix to get us the proper spelling. The one thing I think we might have talked about before or not, but just to make sure, something with hydrogen, for example, like HCl, it is sort of considered more like a type 1 compound, hydrogen, because it can go plus and minus 1. Even though it's technically 2 nonmetals together, we really don't follow the nonmetal rules and naming when we have hydrogen. We think of this as a lot of times H plus and Cl minus. So this would be just hydrogen chloride. So we think of it more as like an ion, even though it really is sharing electrons and nonmetals. Even if you have 2 of them, like H2S, this would be hydrogen sulfide. So once again, hydrogen is sort of an exception. We don't really follow type 3 naming for it. If you got hydrogen that comes up front, you treat it like a type 1 sort of compound. And if you have hydrogen, it comes after the metal, as we talked about, that is when it is the negative version of hydrogen, which is hydride. So even though hydrogen, again, is a nonmetal, it's not really sort of treated like a nonmetal in terms of naming. Any questions on that? All right, so once you name a couple of these, I'll give you some names to write formulas. Let's do dinitrogen. Try sulfide. Let's do carbon tetrachloride. And let's do. Okay, let's take a look at these. So once again, identifying what we got going on, I see a non-metal and another non-metal, which means we just need to roll into the proper prefixes. So I got 2 of the iodines, so we'll go with di for 2, and iodine whole name there for the first guy. Prefix for 7 is hepta. Here we will drop the A and give the second guy the IDE treatment there, so diiodine heptoxide. Next one, looking at it, which is CO2. Once again, here we got non-metal, and non-metal tells us is type 3. Prefix for 1 is mono, but we do not use it on the first name, so we will just use the whole name there, which would be carbon. Prefix for 2 is di, and again, our second guy will get the IDE at the end of it, so carbon dioxide here. Looking at the last one, we got phosphorus, which is a non-metal, and Cl, which is a non-metal. So again, that tells us it's type 3. Mono for the first one, but we're not going to use it, so that's going to be phosphorus. And prefix for 3 is trichloride here. I can spell it there. There we go. Let's see. Any question on any of those names? Like I said, they are the easiest. You just got to pretty much count, prefix, and write. Don't overcomplicate it or anything like that. Probably the easiest of all naming stuff is what we're going to do here on the right, which is write the formula, which means as soon as I see prefixes in my names, I know it's type 3. So I'm just going to write what it says. Di is 2, nitrogen is N, so N2. Tri is 3, sulfide is S, S3. And that would be the formula there. Same thing here. I don't see a prefix, but I do see it on the second one. So no prefix on the first one means it's mono and 1. So I would write C for carbon, and tetra is 4. So that would be a Cl4, and we're done. Yeah. Lastly, here I got a tri and a penta, which is some prefixes, tells me it's type 3. So tri is 3, so that's O3, and penta is 5, and 5 would be it there. And again, I think those are probably the easiest. Just got to write what it says. Yeah. No balancing needed because there's no ions or anything like that. Any questions on type 3, guys? Again, strictly non-metals. These guys are sharing electrons, and we use prefixes here. There is no crossover of prefixes, Roman numerals, or anything like this. So prefixes just for non-metals, Roman numerals just for metals that are multiple charges. No Roman numeral or prefix for guys that have fixed charges. Any questions on any of that there? That should be what that says, I think. That's basically what that comes about there. So again, type 1, no prefix, no Roman numerals. Type 2, Roman numerals, no prefix. Type 3, prefix. All right. Next thing we're going to talk about is actually polyatomic ions, and polyatomic ions are actually groups of nonmetals that are bound together. They are interesting things. They are actually held together through sharing of electrons, so they're actually covalently bonded, but they do have an overall charge. So when we look at something like NH4NO3, it's actually 2 polyatomic ions. The first one is NH4 plus, and the other one here is NO3 minus. That 1 nitrogen and the 4 hydrogens stay together because they are covalently bonded together and are sharing electrons, and it has a +1 charge. Same thing with the nitrogen 3 oxygens. They are staying together, and the overall thing has a -1 charge. We actually drew these two, I think, when we did some Lewis structures. So this is what ammonium looks like here, has a +1 charge. And this is nitrate, which we drew, I think, as well at some point, if I'm not mistaken. Looks something like this. So ultimately, these guys are sharing electrons, but they actually have an overall charge. So really what these guys are really ions, which means we are still putting together something that's positive and something that is negative together to equal 0. And that is why we take +1 and -1, and we just need one of each of them when we put them together to get us our formula here for NH4NO3. So although they are really being shared electrons, they do have charges that are treated like ions. And when we put a polyatomic ion together with something else that has a charge, it needs to still equal 0 when we put it together. These guys have special names. This is the ammonium ion over here. Not to be confused with ammonia, which is NH3 no charge. So ammonia, NH3 no charge, ammonium, NH4 with a +1 charge. So those two get confused a lot. This is the nitrate ion. The good news with polyatomic ions are you pretty much just use the name. So when we put them together, this guy here would be ammonium nitrate. So that's sort of a good thing in a sense. You just use the whole name for the polyatomic ion. And it kind of works like with other things we've been talking about. Even if there's multiple polyatomic ions, it has no effect on the name. So if you had like 2 nitrates, it would still just be called nitrate. Again, we wouldn't use a prefix or anything here and stuff like that. Most polyatomic ions are negatively charged, which means in most cases, the polyatomic ion will be hooked up with a metal. And what that means is we kind of default back to our type 1, type 2 rules here. We would go back to type 1, our type 2 rules, which means if the metal needs a Roman numeral, you should use a Roman numeral. And obviously, if it is type 1, no Roman numeral needed here. So because most of them are negative, we end up with a metal, and we basically just follow the same rules. The metal's still the most important thing. And then the polyatomic ion, you just use the whole name for it. So they really do fall back to sort of those rules. Here's a table of some polyatomic ions. I think there's one up on Canvas as well. But you do need to know these, and there is a way to sort of help you learn them. Most polyatomic ions will either end in ate or ite. So for example, you have NO3-, which is nitrate, ATE. NO2-, which is nitrite, ITE. If you look at something like SO4 2-, that is sulfate, ATE. SO3 2- would be sulfite, ITE. So usually the one that has the most oxygens in a group of 2 will end in ate. And the one with the least number of oxygens in a group of 2 will end with ite, ITE. There are also some that are basically groups of 4, and right about here is our common group of 4 there, kind of coming up that way. This is ClO4-, ClO3-, ClO2-, and ClO-. They're all related to each other. The only difference is the number of oxygens. So they all have a -1 charge. They're all covalently bonded together, just different numbers of oxygen along the way. So you could kind of break a group of 4 up in half, and the ones with the 2 least oxygens will end in ite. So that'll be like chlorite, ITE. This guy would also be chlorite because it has the least number of oxygens, but clearly you cannot have the same name for 2 different things. So when we have a group of 4 that's related to each other, the one with the least number of oxygens will start with hypo and end with ite. So that is hypochlorite, chlorite. You kind of do the same thing to the left. These are the guys with the most oxygens in a group of 4. That is chlorate. This would also be chlorate, but once again, you can't have obviously 2 the same name. So the one in a group of 4 that has the most oxygen will also start with per. So that is perchlorate, chlorate, chlorite, and hypochlorite. There are a group of 4 that are related to each other. Cl is chlorine, which is what's in there. You could actually swap it out for anybody in group 7, and it kind of is named the same way. So if you had BrO3- instead of chlorate, that would be bromate. Yeah, if you put an I in there, that would be iodine and so forth. So you could kind of swap out anybody in group 7 for those guys. Other common things that you see on this table or a table like this is, say, something like carbonate, which is this guy. And sometimes we put an H plus or a proton in front of it, and it becomes HCO3 minus. We basically put an H plus, which is hydrogen. So this is what is known as hydrogen carbonate. Sometimes hydrogen carbonate is also called bicarbonate. So bi instead of hydrogen is used. So sometimes this is just referred to as bicarbonate. You also see that with sulfate. If you put a H plus on it, sometimes called hydrogen sulfate or bisulfate. Again, same idea. When you do put a hydrogen on there, it's not just the H, but it's went from -2 to -1. So +1 and -2 gives you a change in the charge. This goes from -2 to +1 in this particular case. Not all polyatomic end in 8 or I. There are some that end in IDE, like hydroxide, cyanide, azide. There's a bunch of some that do peroxide, which is over here, end in IDE. But a vast majority of them, again, do end in either 8 or I. Sometimes people learn all the 8s and know that if you needed the ite, it's just 1 oxygen less. Everything else is the same, just changes the oxygens, the number charge stays the same. Or you can learn all the ites, and if you needed the 8, you just put on an oxygen. Again, the charge stays the same. So you can remember one of those guys and just know either add an oxygen or take a oxygen, depending on which one that you learn. Yes. You need to know pretty much the ones on this table. I forget if I posted up one on Canvas. If I did, then whatever's up there and whatever's obviously in the book table, which should be similar to this one. But you don't need to know the names. You do need to know names and the charges and the formulas, because that's going to allow you to obviously to put things together properly. So let's take a look maybe at some here. Actually, well, I'll just write some over here. Yeah, we'll go this way, I guess. So let's say we had, we'll do this so we can see the table, I think. All right. Let's take a look at some here. Let's say we had CaNO3 2. Why don't you give the name for that? Let's do FeSO4. Let's do Na2CO3. And let's do some formulas for some names here. Let's do ammonium sulfide. Let's do copper 2 chlorate. And let's do some magnesium bicarbonate. All right, so try some names on the left and try some formulas on the right. Again, think of them really as type 1, type 2 sort of compounds. Again, whole name for the polyatomic ion, Roman numeral, Roman numeral, depending on, which means it has a fixed charge. It's a type 1 compound, which means all we need to do is use the whole name there of the metal. And once again, our polyatomic ion here, we just use the whole name of it as well. So this would be calcium nitrate. Once again, the 2 has no effect on the name here. The reason we do have a 2 there is because we need, the cation here is calcium, and we do need not one of these -1s, but we do need 2 of these -1s, right, to balance out the charge. That's -1 and -1 is -2. That balances out our +2 charge. The other thing that we see in this formula is there are parentheses around the polyatomic ion. We do need to use the parentheses around a polyatomic ion when there is more than one, because if you just did this, that means what? 32 oxygens, which is really not what you mean here. You mean you have 2 units of NO3. So whenever there's more than one polyatomic ion, you do need to put parentheses around the polyatomic ion, and you do need to put the number on the bottom. Question on that name there. Coming down here, this is iron, which is a metal. That is sulfate, which is a polyatomic ion. It is our type 2 metal here that we need to worry about. So iron here, not sure what the charge is, but I do know that my sulfate is -2 in this case. That means that the iron needs to be +2 to balance it out. And that means that this would be iron, Roman numeral 2. And again, the whole name for the polyatomic ion, which would be sulfate. Again, the 2 there for the charge on the metal, just like we did with type 2. Question on that name there. Coming here, that is sodium, which is a metal, and carbonate, which is a polyatomic ion. Once again, the metal is most important. Sodium is group 1, which means it's type 1, which means I don't need a Roman numeral. So I just need to write sodium and carbonate, the whole name of the polyatomic ion. Any question on any of those names there? Now, let's take a look at the formulas. They are basically ions. So we're just going to put our positive negatives together. Ammonium is NH4 + 1. Sulfide is actually from the periodic table. It is sulfur with a -2 charge. That means in this case, we actually need more of the NH4+. We need one more of them to balance it out. And because we have multiples of the polyatomic ion, we also need to put a parenthesis around it. NH4, a 2 on the bottom, and 1 sulfur in this case to basically balance it out. Any questions on that one there? Looking at the next one, I see copper Roman numeral 2, so that automatically tells me my copper has a +2 charge. Chlorate is this guy right here, and that is ClO3 -1. In this case, we're putting together -1 and +2. We actually need more of the chlorate, and we need 2 of them to get us to -2. Once again, because that is the polyatomic ion, we will need to put parentheses, the ClO3 in the parentheses, and a 2 on the bottom. And that would be the proper formula. That basically says we have 2 of these guys happening. -1, -2 gives us +2, -2 equals 0. Question on that one there. Lastly, we have magnesium, which is a metal. Bicarbonate, which is a polyatomic ion. Magnesium is group 2, which means it has a +2 charge. Bicarbonate is the same as hydrogen carbonate as we see here, and that is HCO3-. So once again here, we're taking a -1 and a +2 and putting it together. That means that we need not one of the -1s, but we need one more there to balance it out. That also means that's a polyatomic ion, so we need some parentheses. So we're going to do something like this, where we put the 2 on the bottom. Any questions on any of those formulas? Now, one last thing here before you finish on this was I did mention that there is really no place where a Roman numeral and a prefix would come into play. The only time that that would happen is if you had a type 2 metal that may be hooked up with a polyatomic ion that already had a prefix in its name. So it's not a prefix that you would put in there, but it's part of the name. So, if you had a polyatomic ion and that's dichromate, obviously that would be the only place where you would have like a Roman numeral and a prefix together. Any questions on that?